Okay, so let's think about a couple other considerations that might be important to include when we are scheduling power plants in order to meet electricity demand. And the first one is transmission constraints. So let's say we have a network, a system of connected nodes and transmission lines. And you could think about the nodes as places where people are demanding electricity, as well as places where power plants are that could be producing electricity. And let's say we have an abundance of cheap electricity in the Pacific Northwest, and we want to get it all the way down to Los Angeles to meet high demands for electricity. So not that might not always be possible. We might be able to send some electricity down from the Pacific Northwest into California, but not as much as we'd like, and that's because of transmission congestion. The way to think about it would be that high voltage transmission lines have a certain amount of electricity that they can carry at one time. And we can exhaust the limits of what's possible to send. Just the way we can get traffic jams on highways with people in cars, we can get traffic jams or congestion on transmission lines that might prevent us from sending electricity to exactly the place that we want to send it. Another important consideration are forecast errors. So for generation is generally scheduled at plants 24 hours in advance. And that's for all sorts of good reasons. You don't want to leave this important decision to the last minute. And so, to the extent possible, a lot of the scheduling is done in advance. However, electricity demand is slightly different every day. And so, what explains this? Well, the answer is weather. The biggest drivers of day to day changes in electricity demand, especially in the winter and the summer, are changes in temperature. Hotter days in the summer have higher electricity demand than cooler days, and colder days in the winter have higher electricity demand than milder days. So this raises an issue because we're trying to make decisions 24 hours in advance about how to schedule generation at power plants, and we know that we're making that decision about how much demand is we're going to need to meet based on a weather forecast. And the good news is that when we're trying to forecast weather 24 hours in advance, we're actually really good at that. We can predict the weather with about 93% accuracy, at least in terms of temperature, 24 hours in advance. However, that does leave some room for error. We might get it wrong. We might expect the temperature to be really high and it doesn't materialize and it's a little bit cooler than we thought. Or we might think that the temperature is going to be mild and it actually turns out to be a lot hotter. And because of the way that temperature can control electricity demand, what that means is that the amount of electricity demand we forecast to need to be able to meet could be somewhat incorrect. And that could mean that the amount of generation that we schedule out into the future might be a little bit incorrect as well. So demand on the timetable of power system scheduling, which is about 24 to 48 hours, is a little uncertain. And increasingly, we also have to deal with sources of uncertainty on the supply side, both in terms of wind power, which can be impacted by less than or greater than expected wind speeds, as well as solar power, which can be impacted by cloud effects. So demand is a little bit uncertain, and sometimes when we forecast it, we can be wrong. And also, our supply of variable renewable energy can be a little uncertain. Is there another reason to be a bit conservative when scheduling generation? Well, in just the same way that we talked about the issue of unexpected impacts on reliability, plant reliability, when we were talking about long-term system planning, needing to have a reserve margin in case power plants did not work when they were supposed to, we also need to account for that risk when we're making short-term plans. And so this is just a figure that shows on the y-axis reliability, where we're defining reliability as the probability that a plant will actually work when you want it to, and years of operation. And what it suggests is that the longer a power plant is operational, an older power plant, the lower its reliability is. In other words, the higher the chance is that when you go to try to use it to produce electricity, it's just not going to work. And so this is sort of a fact of life in the electric power industry. Sometimes power plants don't work. So in order to ensure system reliability, which we're defining here as the ability to meet electricity demand in every hour, operators typically will set aside some operational reserves in case something goes wrong. And so operational reserves are generation capacity that's left unscheduled on purpose. And this capacity can then be used to address unexpected losses of power plants. So what determines demand for operating reserves? Well, it can be a little complicated, but a simple rule of thumb is called the N-1 criteria. And so what this means is that at any given point, you want to have enough reserves, backup generating capacity that's online, ready to produce electricity, to replace the single largest power plant online at any one time, and that's often a big coal or nuclear baseload power plant. So another way to think about this operating reserves would be Homer insurance.